In this 20th podcast, we're going to be taking a look at the second of Newton's three laws of motion. But let's quickly recap what the first law states. The first law states that if the forces on an object are balanced, if there's zero resultant force, then the object remains in constant motion. So this ship, for example, up and down forces are equal in length, so they cancel out. Left and right forces are equal in length, they cancel out, so the ship continues doing what it was doing, which is probably moving to the left. In this situation here, we can see a person standing stationary on the ground. Their weight is balanced exactly by the reaction force, and they don't move. Their motion remains constant. If the forces are not balanced, there is a resultant force, and the object does not remain in uniform motion. Let's take a look at the ship again. So again, the weight is balanced by buoyancy. The blue arrow represents the upward force, we can call that buoyancy. But the left and right arrows are not equal in length. The left arrow, presumably the force from the ship's engines, is not balanced by the friction force, the pink force, probably the drag of the water. Let's take a look at the force vectors there. So the upward force added to the left force, added to the downward force, added to the right force, the shape doesn't close, telling us that there's a resultant force. And the resultant force is a vector drawn from the start of the first arrow to the end of the last arrow. So this black arrow here will close the shape and is the resultant force. Now we know that the up and the down forces cancel out, so we can technically ignore those. And we can see that the resultant force is going to be 14,000 to the left, minus 10,000 to the right, which is going to give us 4,000 newtons. 4,000 newtons. So the resultant force is 4,000 newtons to the left. Now that resultant force will cause the boat to accelerate in the left direction. Now what Newton showed in his second law is that the resultant force on an object is proportional to the object's acceleration. Double the resultant force, double the acceleration, and so on. So let's take a look at the ship again. Now in this case, we've increased the force to the left, the thrust from the engines. The up and down forces have remained the same. We've now got 18,000 newtons to the left, and we still have 10,000 newtons to the right. Now in this case, we can see now that the resultant force is 8,000 newtons. 8,000 newtons to the left. A greater resultant force, greater acceleration. Now we can see actually that it's double the resultant force, so we can expect from Newton's second law that the acceleration is also going to be doubled. And Newton went on further and discovered that the object's acceleration also depends on its mass. A bigger mass leads to a smaller acceleration. Let's take a look at this race here. Now we've got two cars, very similar cars, but one is smaller than the other, less mass than the other. They both have the same engines though, so they're going to both have the same maximum push force. The orange arrow represents the push force from the engine. The up and down arrows represent weight and reaction force, but they cancel out. Likewise here. So we have the same push force from each car, but the top car has less mass than the bottom car. So we can expect from Newton's second law, the top car to have a greater acceleration. This arrow here, this double-headed arrow, represents an acceleration vector. This acceleration vector is longer than this acceleration vector. So let's try and quantify these relationships in Newton's second law by looking at an applet by the PHET team at Colorado University. So this is a screenshot from the applet we're about to look at, and we have an object, a crate, and a person who's going to be pushing the crate with a given force. The graphs below are going to show how the force changes with time and how the acceleration changes with time. So we'll be able to monitor the force and actually see what the acceleration is. We're going to record our data in this data table here. We've got force in newtons and acceleration in meters per second squared. So here's the applet, the crate and the person, and the force. I can change the force here. I can put in the force that I want. And I'm going to start off with 200 newtons and see what happens. Click go. We can see the force being applied and the object accelerating to the right. Let's take a look at the data there. I'm just going to rewind. So we can see that for a total force of 200 newtons, and I've switched the friction off, I'm pretending there's no friction. With a total force of 200 newtons, we have an acceleration of 0.7 meters per second squared. So going back to my data table, I can put in that data. Let's apply 400 newtons this time. 400 newtons. Go. I'll pause it there. So we can see now that with an applied force of 400 newtons, we have an acceleration of 1.3 meters per second. So I'm going to go in and put that into my data table. 400 newtons, 1.3 meters per second squared. Go back in and now type in 600 newtons. And pause. And look at that data there. With an applied force of 600 newtons, we can see we've got an acceleration of 2 meters per second squared. Let's put that data into the table. Now I'm going to go in and put in 800 newtons. And pause. We can see with 800 newtons we've got an acceleration of 2.7 meters per second squared. Put the data in. And finally, I'm going to put in 1000 newtons. And with 1000 newtons applied force, we can see we have 3.3 meters per second squared. So let's put that data in. And there we have it. Now we can see that the data is going up, the force is going up, the acceleration is going up. And just to see if there's a constant relationship between the data, I'm going to divide the force by the acceleration. And in this third column, I've got the force divided by the acceleration. So 200 divided by 0.7 gives me 286. 400 divided by 1.3 gives me 307. Not the same, but close. 600 divided by 2 gives me 300. And we have 296 and 303. Now we can see that all these numbers are virtually the same within 10 or 15. They're about the same. So we can see that there is a constant relationship between this data. We can see that the force is proportional to the acceleration. Now we can see that much more clearly if we actually plot a graph of acceleration, the dependent variable, against force, the independent variable. We get a straight line through the origin, so we can see that the two variables are proportional. As well as the straight line telling us that the variables are proportional, we can also see that the slope of the graph, the rise over run, the rise over the run is going to be the acceleration divided by the force. So the slope is acceleration over force. We can rearrange this equation here, multiply through by force and divide through by slope, and we get force equals acceleration over slope. But from the experiment we did with the applet, the third column, which was force divided by acceleration, gave us a constant value. And this constant actually turns out to be the object's mass. Let's go back and just check that. So here's the applet. I'm going to slide it over a little. And we can see the crate actually has a mass of 300 kilograms. Now this is also the inverse of the slope. Force over acceleration is a constant that we've just shown as the mass, force divided by acceleration. But if I go back and have a look at what the slope is, the slope is acceleration divided by force. It's the opposite way around. So the mass is actually the inverse of the slope. So finally we can say from previously. The force equals the acceleration of the slope, but the slope is the inverse of the mass. So we have force is the acceleration divided by the inverse of mass, which becomes force equals mass times acceleration, which is one version of Newton's second law. It tells us that the force is proportional to the acceleration and that the constant of proportionality is the mass. So to summarize, zero resultant force means zero change in motion, not zero motion. The resultant force gives rise to acceleration, or a change in motion. The resultant force is proportional to the acceleration, and the acceleration is also proportional to the object's mass. And in general, this can be summarized with Newton's second law: force equals mass times acceleration.